So in this video, we'll be discussing questions from quantum mechanics which appeared in your CSIR NET December 2019. So 7 questions were there which appeared from quantum mechanics. So in the first part, I'll be discussing the first 3 questions, and in the second part, I'll be discussing the remaining 4. Okay. So the first question which appeared was 2 interacting particles were given, one with spin 1, the other one with spin half, right? And then the Hamiltonian for the system was given to be this. Now what we need to do is, what we are asked to find is the largest eigenvalue for this Hamiltonian, right? Okay. So now how do we start, right? So what we are asked is, we are asked to find this, which is energy, right? So what we need to do is find the expectation value of this Hamiltonian, which is nothing, which will actually give you the energy. So what we need is, to solve this problem is, we need to know the eigenvalue of s square, which is s into s plus 1 h cut square, the eigenvalue of sz, which is ms h cut, right? So this m is corresponding to your spin, and sx square is given by h cut square by 2, s into s plus 1 minus ms square, right? Okay. Here we have two particles with different spins. So the total spin is given by S1 plus S2. So if I square this, so I'll be left with S1 square plus S2 square plus 2S1 dot S2. Hence I can find out S1 dot S2 expression from here, right? Half S square S1 square minus S2 square. So here S1 meaning the spin angular momentum for your particle 1, and S2 meaning the spin angular momentum of your particle 2. Right? Now these are the particles. So if I want to know what is the spin for your S1 particle 1, it is 1, and for second particle it is half, right? So the total spin which corresponds to your, so you had 2 spins, right? So S1 corresponds to this and this one corresponds to this. So the total spin S is given by, so this S is given by S1 plus S2 up to S1 minus S2, which is 1 plus half, which is 3 by 2, in steps of 1, S1 minus S2, which is half. And because I am asked to find the largest eigenvalue, what I do is I take this S to be 3 by 2. Okay. So now moving to this problem. Okay. So the first part is A. So H I will be replacing with this, right? So from first part, so S1 dot S2 I will replace with this. So 1 by 2 comes out because these are constants. So I am left with Sm. So H is given by that, so which is S square, S1 square minus S2 square Sm, right? Plus B Sm S1x plus S2x. Okay. Now I need to make use of these formulas, right? So A by 2. So S square acting on Sm will give me S into S plus 1 h cut square. So it is S into S plus 1 h cut square, and S1 here, S1 square, right? Again it is given by S1 square. So it is S1 into S1 plus 1 h cut square plus, okay, minus, for S2 again it is given by S2 into S2 plus 1 h cut square. So this was the first part, right? So now the second part is B. It is S1x acting on Sm. So for the first particle it is h cut square by 2. So because it is just S1x and it is, the formula is given the square, so I need to have h cut by root 2 square root of s, because it is for 1, hence 1, s1 plus 1 minus n corresponding to spin 1, right? So similarly for the other one, which is plus, is given by h cut by root 2 square root s2 plus 1 minus ms2 square, right? So now the task is very easy. So you have a by 2. So now this s is corresponding to the total spin, this one, right? So which is 3 by 2. So 3 by 2 and then s plus 1, which is 5 by 2. So there is h cut square everywhere, so I'll just take that h cut square out. So 5 by 2 minus s1. So s1 is 1 here. So 1 into 1 plus 1, which is, let me just write it as 2, minus, I have s2 as half. So that gives me half into half plus 1, which is 3 by 2, right? So I'm left with b. So let me take out h cut by 2 also common. So h cut by 2, and then I have square root of, so s1 here is again 1 into 1 plus 1, which is 2 minus ms1 square plus square root of, so s2 is half into half plus 1, so 3 by 4 minus ms2 square, right? So I've got this. So I've got my E to be, so this yields a h cut square by 2. So the term here, the whole thing equals 1. Okay. So that gives me plus b h cut by root 2 square root of 2 minus ms1 square plus square root of 3 by 4 minus ms square. Okay. So this, so we need to know what is ms1 and ms2, right? And we also must keep in mind that we are asked to find the largest eigenvalue, right? Okay. So s1 is 1. Right? So ms1 will be plus 1, 0, minus 1, right? s2 here is half, so my ms2 will be plus half and minus half, right? Okay. So first let me check this E for ms1 equals to 1 and ms2 equals to plus half or minus half. I mean both plus 1 and minus 1, and both ms2 equals to plus half and minus half will give me the same result, because I have ms1 square and ms2 square, right? So plus minus doesn't make a difference. So E in that case is given by a h cut square by 2 plus b h cut. So if you calculate, you'll be getting square root of 2 plus 1. So E is this for your ms1 as plus minus 1 and ms2 as plus minus half. And for ms1, the next condition is, because I have 0 as well, right? So for next condition 0, both plus minus half here, I get E to be a h cut square by 2. Let me rub this. I get a h cut square by 2, b h cut by 2, and if I substitute these two, I am going to get a term 3, right? So, and if you see here, this term is smaller than 3, and because I am asked to find the largest eigenvalue, so my answer is this, right? So I go ahead with this one. So it is 1 by 2 a h cut square plus 3 b h cut, right? So this is the required answer. So what I did was, I took the Hamiltonian, I found the expectation value. I was given two spin particles, right? One with spin 1, the other one with half. I found the total S, which came out to be, because I was asked the highest eigenvalue, I took it to be 3 by 2. My S1 anyways is half, S1 is 1, S2 is half. So based on this, I found the corresponding values for your S square, right? The eigenvalues for S square, S1 square, S2 square. Similarly, I did for S1x and S2x, and then after finding this, I had the choice for MS1 and MS2, right? And because I was asked to find the largest eigenvalue, I went ahead with MS1 equals to 0 and MS2 could be anything plus or minus half. Hence, your answer is this. The next question, in question number 2, what you have is, you are given a wave function, right? Your particle is in your one-dimensional potential, and the wave function is given here. What we need to do is, we need to find the expectation value of the energy. Basically, you need to find, so basically we need to find this. Okay. So what we do is, so this thing here can also be written as 8 by 5 sine pi x plus half sine 2 pi x. I mean, this is nothing new. I mean, what I have done is, I have made use of sine pi x, cos pi x, right? Sine a, sine b is given by 2, sine 2ab is given by 2 sine a, sine b. That formula I have used. Okay. So what we need to do now is, we need to find this, and it is given by, okay, and this is valid for your x between 0 and 1, right? So my integration limit is going to be from 0 to 1 psi, which is square root of 8 by 5 sine pi x plus half sine 2 pi x, right? And h here is given by minus h cut square by twice m, d square by dx square, and again square root of 8 by 5 sine pi x plus half sine 2 pi x, right? So I can take my h cut square by twice m out, and root 8 by 5, root 8 by 5 out of the integration, right? Okay, this is over dx. So that gives me 8 by 5 minus h cut square by twice m, right? So this 2 and 8 cancels, and it gives me 4 h cut square by 5m. So what I need to do is, I need to find d square by dx square, double derivative of this term. So ddx of that, okay, let me write it as psi, is given by, I mean, this is simple differentiation, right? It's given by pi cos 2 pi x, and d square psi by dx square is given by minus pi square sine pi x plus twice pi square sine 2 pi x, right? So what I need to do is, I need to substitute this over here. Instead of this, I need to have this, and then perform my integration, right? So which is minus 4 h cut square by 5 m integral 0 to 1 over dx, right? So I have sine pi x plus half sine 2 pi x, and then this one which is minus pi square, so I take out minus pi square outside, so this becomes plus and my pi square hangs here. Then I have sine pi x plus half sine 2 pi x, right? So that gives me 4 pi square h cut square by 5m, and then the integration of sine square pi x plus sine square 2 pi x, and this two terms here is going to give me, okay, this is actually 2 sine 2 pi x, so that's going to give me 5 by 4 sine pi x and 5 by 2 sine pi x and sine 2 pi x, right? So this is sine square pi by x, and then this term gave me sine square 2 pi by x. The cross term gave me this one, with this is 2, and then this with this is 2 plus half is 5 by 2, right? So this whole thing gives me, the integration is the integration value is 1, hence my energy is this, my energy comes out to be 4 pi square h cut square by 5m. So that is the answer for your second question, where I was asked, so the wave function was given, I was asked to find the expectation value of the energy. What I did was took psi h, psi expectation value, h I have replaced by minus h cut square by twice m d square by dx square, found the double derivative of the wave function given, and then it's all simple integration, and then the integration limit is from 0 to 1, right? So this is my answer, which is 4 pi square h cut square by 5m. Now moving on to your third problem. So wherein a Hamiltonian is given. So the Hamiltonian is given to be 2 1 0 1 2 0 0 0 2, right? And the states, the eigenfunctions, the eigenstates are psi 1, psi 2 and psi 3. These states are normalized, right? What we are asked to find is, we are asked to find the expectation value of the Hamiltonian and the variance in the state psi, right? In the state psi, which is given by 1 by root 3 psi 1 plus psi 2 minus I psi 3, right? So the states are given, right? So the state where I need to find the expectation value is this one, and also the variance, right? So how do I go about with this problem? What I need to do is, so this is the ket, the bra is given by 1 by root 3 psi 1 psi 2, because it's a star, right? I mean, if you have this and then this is given by the conjugate of this, right, star, so hence plus I psi 3. Why have I done this is because if I am finding h, right, first let us calculate h and then we will discuss about the variance. So the expectation value is given by psi h psi, okay. So I need to find this, wherein I will be making use of these two. Here I must understand that my Hamiltonian is given in terms of a matrix which is 2, 1, 0, 1, 2, 0, 0, 0, 2. Hence, what I'll do is I'll write my bra and ket also in terms of a matrix, right? And that is, the ket is given by, the same thing is given by a column vector, right? And the bra is given by your row vector. Meaning, if I am writing this, then I will have 1 by root 3, right? This one is given by a column vector. So 1 by root 3 psi 1, 1 by root 3 psi 2, I by root 3 psi 3, right? And this side here, the ket is given by a column vector which is 1 by root 3 psi 1, 1 by root 3 psi 2, and I have minus I by root 3 psi 3. So, finding the expectation value of H boils down to calculating this matrix multiplication, right? So, it is given by your row vector, and then first we will multiply this, which is given by 2 by root 3, right? This is 2 by root 3 psi 1 and 1 by root 3 psi 2. Then here we have, so this is 0, right? So then we have 1 by root 3 psi 1 plus 2 by root 3 psi 2. Again, this gives me 0. So this is 0, 0, and again minus 2i by root 3 psi 3, right? And then I have this, which is 1 by root 3 psi 1, 1 by root 3 psi 2, and 1 by root 3 psi 3. Okay. So, meaning this boils down to this multiplied by this. That means 1 by root 3, this part multiplied by this here. So this is 1 by root 3 into 2 by root 3. So 1 by root 3 into 2 by root 3, right? And then we have psi 1, and because the states are normalized, right? So psi 1 gives me 1, right? Because the states are normalized, psi 1 gives me 1. And then again I have with 1 by root 3. So this is the first one. Then I have 1 by root 3, and then I have psi 1, psi 2. Two different states, they are normalized, hence this gives me 0, right? Plus, now this second term with this one, which gives me 1 by root 3, right? So again, if I am multiplying psi 2 with psi 1, that gives me 0 because the states are normalized. So hence 1 by root 3 and 2 by root 3, psi 2 will give me 1. So it is 1 by root 3, 2 by root 3, right? So this is the second term found by multiplying these two. Then I have my this term multiplied by this, which gives me 1 by root 3 and minus 2i. Okay, this was actually I by root 3, right? So it is I square minus. So minus into minus plus. So 2 and then root 3 is 3. So it is 2 by 3. This is also 2 by 3. And this is anyway 0. So this is also 2 by 3. So I am left with 6 by 3, which is 2. That means my expectation value of h I have found to be 2, right? Okay. So this is for the first part, which is finding the expectation value of the Hamiltonian, right? Now we need to find the variance, which is sigma square, which is given by h square. The expectation value not of h but of h square minus h, expectation value of h the whole square, right? This I have already found, which is 2, and then 2 square is 4, but then I have to find again the expectation value of h square, meaning I square my Hamiltonian, multiply the two matrices, right? And then I get 5, 4, 0. The multiplication is simple. 4, 5, 0 and 0, 0, 4, right? And then for finding h square, what I do is, again, I write my column vector, right? Which is the same old matrix, which the same old state, which was your psi 1 plus psi 2 plus I psi 3, right? So that is your, okay, it was minus I psi 3. So I write my column row vector, then I write my Hamiltonian, this one, the h square one, and then again I write my column vector. So when I multiply, I am going to get this. I mean, it's similar to what I have done with h. So this I find to be 14 by 3. So that gives me my variance to be 14 by 3 minus h square, so which is 2 square, which is 4. So this comes out to be 2 by 3. So my h came to be 2 and my variance came to be 2 by 3. Right? Okay. So this was your third question. Right? So I hope this is clear. So what was given was the Hamiltonian was given in the matrix form, and the states in which I had to give, I had to find my the expectation value was given as a linear combination. So what I can do is, when I have my ket can be replaced by a column vector and my bra can be replaced by a row vector, and then it's simple multiplication of the matrices. That's how I solve this problem. Thank you.